Good morning. All right, I am no better for the time change. All right, well, if you were lucky, yesterday afternoon, you had a chance to see me walking Sadie around campus a little bit. If you were really bold, you were lucky enough to actually have your picture taken with Sadie. So, yeah. All right, so. Let's see. An announcement. I'm going to have to change things up a little bit. And so this actually, I hate this a little bit, but ever since I got to William & Mary, I've taken a lot of pride in making sure I can give a lot of individual attention to people whenever they need it. And I don't think anyone's ever been discouraged from popping into my office for a meeting. That said, I've never had 300 plus students before, and I've realized over the last 24 hours or so that going forward, I envision that a lot of one-on-one meetings aren't going to be that possible. I'm going to find myself in a situation where I just don't have any time whatsoever, and I'm going to have to start turning people away. That said, I don't want to do that, and so I've done a little brainstorming, thinking about how I can basically use my time most efficiently. And so what I've come up with, so we've got the workshops, and I have a feeling those are going to be better attended as we move forward with the material that we're seeing. Furthermore, I think instead of trying to do individual appointments, and trust me, if you have something that you need to talk to me about individually, I'm still 100% available and will do so. But to make myself available to as many people as possible and to reach as many people as possible, I think I'm going to start holding one office hour each day in a conference room. I'm going to stagger these so that hopefully you'll have availability for at least one of those hours. I'm guessing you'll have availability for, or at least most of you will have availability for several of those hours. But that way I can make sure that as many people as possible are getting their questions answered. I realize that there are still some sensitive things that you might want to discuss, such as grade topics. In that case, we can definitely still meet one-on-one, but I want to make sure that I'm able to give everyone as much attention as possible, and that's not going to happen if I end up having to turn people away because I don't have slots in my schedule. So I'm going to work on getting a room scheduled. I'm going to do this in a conference room somewhere so that we can hopefully pile in if there's a lot of people that would like to ask some questions and things, and so hopefully that'll be the most efficient way we can do this going forward. So, if I have a meeting scheduled with you this week, I'm not canceling that meeting, but just understand that I'm going to have to be a lot more selective in scheduling things as we go forward, just because I have no time left. So that's the plan moving forward. Okay, so let's see. Last time we were talking about regioselectivity and regiochemistry. We learned about Markovnikov's rule, which basically said that our electrophile, and in most cases, our electrophile is going to be a proton whenever we're reacting with an alkene with in a carbocation type mechanism. And so we learned Markovnikov's rule. This is basically the proton is going to add to the carbon with the most H's, more or less. You can easily remember that as well. The proton is going to join its friends, the other H's. Now, I had a few questions. One of those questions was, well, when we look at this example right here, there's actually, I guess, 6 protons on the left side of the compound and 2 protons on the right side, right? But we're only worried about protons that are directly connected to the carbons involved in the alkene. And so, in reality, this left side, we say it has no hydrogens. This side has 2 hydrogens. And so, what we're going to find is our proton will want to come over here and be with its friends. And so we end up with this carbocation. And ultimately, the reason we follow Markovnikov's rule is that this is the more stable carbocation. And so that's the preferred mechanism. All right, so then we showed an example of that, Markovnikov regioselectivity with this example. So we've got an alkene with a tertiary carbon and a primary carbon. And so it'll be nucleophilic. It will go after this proton as such. And so we end up adding that proton to the primary carbon, again, just following Markovnikov's rule. That gives us a tertiary carbocation. And so eventually, for the second step of our reaction, we're going to snap together our charges, and so our chlorine is going to go straight for that carbocation, and that's why we get the connectivity that we end up seeing. All right. Our song today was really struggling with these song choices today. That's all I'm going to do is give you one reason. So there's a lot of products possible, and so hopefully by the end of the day, today, I will have given you all the reasons that we're going to see different products, and then basically we'll spend the last 4 lectures before the exam talking about different reactions, but at that point you'll kind of know the background, and so hopefully it'll sort of explain itself as we go, and this will end up being a very fluid week and a half or so we have left. Okay, so I'll start out with another example today. So I like drawing alkenes and rings because I think it allows us to see the stereochemistry a little better. So you'll see a lot of these examples I do end up being cyclic alkenes, or I guess cycloalkenes. So in this example, we're going to use, let's draw this a little differently. Let's draw it, our oxygen on that side, and our alkene there. Okay, so first off, the carbons involved in our alkene, that top carbon, what kind of carbon is it? How many carbons is it connected to? 1. 1, and so it is a primary. Yeah, so we've got a primary. And so the bottom one, what is it? Secondary. That's a secondary. And so what we're going to do is we're going to treat this with, use HBr this time. So again, it's just a strong acid, and we don't always have to use HCl. We can use HBr or HI. And so the first step of this reaction is going to be what? Yeah, it's going to be protonation of the alkene, right? We're going to use the nucleophilicity of our double bond, or our pi bond, to reach out and grab the proton. So, again, mechanistically, every time we do a carbocation reaction, the steps are going to be the same. We're going to start with the alkene, and we're going to draw our arrow to the proton. All right, so of course our bromine will go away. Now, our possible carbocations that we could form. We could form this carbocation, or we could form this carbocation. Now, we've said all along that when we think about carbocations, we often are going to follow Markovnikov's rule, which is based on the more stable carbocation. But in this case, what's going to be our more stable carbocation? Will it be the secondary carbocation or the primary carbocation?
Secondary.
Things we need to think about as we go forward is keep in mind that resonance can change things up a little bit. So even though we have a primary carbocation here, and following the strict sense of Markovnikov's rule of adding the hydrogens to the carbon with the most hydrogen, remember, resonance trumps any of these substitution rules. And so in reality, what is our more stable carbocation, the primary or the secondary? Definitely the primary, and it's because we have a closed shell carbocation, and anytime we can have a closed shell carbocation, that's going to be more stable. So the product we end up forming will be the product that attaches our bromine to that primary carbocation. So what we end up with is this product right here. So I guess the point of this is be on the lookout for resonance. Okay. So that'll pretty much end our regioselectivity section. The next thing we'll talk about is going to be stereoselectivity as it pertains to carbocation mechanisms. All right, so let's see. Let's draw an alkene. So the way we're going to draw this, let's draw it on edge. So we're going to draw the plane depth coming towards you. So we end up with, let's say, on this side a proton. On this side, over on this side we'll put methyl groups. So we'll put HC3. And HC3. Of course, and when we draw an alkene with this sort of orientation, where do the p orbitals go? Those p orbitals go straight up and down. So there's our pi bond right here. And so pick an acid. You use HCl or HBr or HI. HI, yeah, good one. All right, so I guess it's a good. I don't know. I think anyone actually uses HI or anything, but I don't know. All right, so our double bond, of course, is the interaction between each of these lobes of the p orbitals. How many double bonds is this? How many pi bonds is this? It's one pi bond, right? It's just got 2 lobes, and so we have 2 areas where there's overlap, giving us the stability that is the bond. All right, so when we attack that hydrogen, all right, think about the shape of our pi bond. We actually have 2 areas that those electrons could be as we undergo the attack, right? So what we could do is we could say, well, maybe it's going to be up here as we attack that hydrogen. But it could also be on the bottom, right? It could also attack from this bottom face right here. And so what we're going to find is we get two different possibilities of addition of this proton based on the fact that that pi bond has electron densities on both the top side of our plane as well as the bottom side of our plane. All right, so our red product. And so which carbon will we add our proton to? The one on the left or the right? Definitely the one on the right, right? We're going to follow Markovnikov's rule, and so it's going to join that proton. So what's going to happen is that new proton, we'll draw it in red here, is going to add from the top, which basically pushes these two protons downward. All right, so these are going to kind of get pushed down. And so in effect, what we end up seeing is a structure that looks like that on the right side, right? So we've added our proton from the top side of that carbon on the right, and so it's pushed the other two things down. And so nothing's changed, of course, on the other side. Well, other than the fact that we now have an open p orbital, which accounts for our new carbocation. All right, so we've got plus there. All right, so let's see, I'm running out of screen. Let's go down for our blue example. And so in our blue example, if we add the proton to the bottom face, well, which carbon are we going to add the proton to?
Still this right one.
Still the right side. We're still following Markovnikov's rule. Regioselectivity is not going to change. We still want to form the more stable carbocation. But what's going to happen is now we're going to add that proton to that bottom lobe of the p orbital. And so in doing so, let's see, let's draw it like this. So now it's on the bottom side. And so if it's on the bottom side, where do those protons that were already there, where do they get pushed? They get pushed up, right? Because we're essentially turning this sp2 hybridized carbon into an sp3 hybridized carbon, and so we should end up with tetrahedral atoms. And so that's what we see. So now we've got our hydrogens that have been pushed up, just like that. And again, on the left side, we're going to have the same picture. We're still going to have an sp2 hybridized carbocation. All right, so that's all fine and well. So at this point, let's see, what do we want to do next? What we've got to think about is the fact that we still have our iodine floating around with a negative charge. Now, what's the next step of this mechanism? All carbocation reactions here, or at least what we've seen thus far, are two-step reactions. We protonate, and then what do? We snap together, right? We have a halogen, and then it snaps together to our carbocation. So that carbocation, how many lobes does it have for that p orbital? It has two, and so what could happen is it could attack from the top, or it could also attack from the bottom. And so we actually end up with multiple possibilities here. So we could add here from the top, or we could add here to the bottom. All right, so of course that leads to two different products. So our green arrow, we'll just go straight down to save some room, is adding from the top, and so we're going to end up with our iodine that has pushed our methyl groups down. And then what's happened to the right side of the molecule? Nothing. It stayed the same. We're not doing any chemistry on the right side of the molecule in this step, so we're still going to end up with just a CH3 group here. Okay, so alternatively, we could add to that bottom lobe, and so if we add to the bottom lobe, we want to show our iodine adding from the bottom, which pushes our methyl groups to the top. And here's the good news. It doesn't get messier than carbocation reactions. All right? All the reactions that we learned in hash carbocation are going to be more simple. They're going to have better regioselectivity and definitely better stereoselectivity. So carbocations, we find, are not the most ideal reactions in the world because they're planar, and so the first step we can have attack on the top side and the bottom side, and then even the second step we can have attack on the top side and the bottom side, and so we end up with a lot of different possibilities. So we have the right side has not changed, so we end up with this right here. Okay, so in a similar fashion, our iodine can attack from either side up here. So we've got iodine, so we can either attack from the top side here, to the bottom side here, and so we end up with very similar looking product. So if we, in our green product, we've added to the top side, so we end up with iodine on top. The alternative is that we add iodine on the bottom. So that will look like this. Now, when we look at this material, I made this relatively simple on purpose. So, what's the relationship between all these molecules? Are they stereoisomers? Do we have any chiral centers? We don't, right? And because of the starting material that I gave you, what we find is that these are actually all the same molecule. They only differ by bond rotation. We can simply rotate that single bond. And so really what we've got here, even though we had 4 different mechanistic paths, is we've got all the same product. But what we're going to find is that sometimes we don't start out with simple starting materials that spit out the same product going either of the 4 directions. And so those are the cases where we can have multiple products. So in this case, only one product. But that's not always true. Okay. All right, so for an example of where we end up with different products, let's look at, let's see. Let's start out with this, and I'm going to use this material a lot because it gives us a pretty clean picture of what our stereochemistry is. So we're going to react this with some electrophile, nucleophile combo. And so what happens is when we do that, we know that our first step is we're going to take our double bond. Always our first step in a carbocation, we start an arrow at the alkene, and we move that towards the electrophile, which is most typically a proton, right? That's basically the electrophile we'll ever see when we're doing these sorts of reactions with carbocations. And so what we've got, of course, is, well, first off, which carbon will our electrophile add to, following Markovnikov's rule? Yeah, so we've got a tertiary and we've got a secondary, and so we know that the tertiary carbocation is going to be more stable, and so by adding our electrophile to that bottom carbon, we're going to end up with a more stable carbocation. So, of course, the hybridization of this secondary carbon is what? It's sp2, right? Which means it's planar and it has a lobe coming towards you and it has a lobe going away from you. And so our electrophile can add to either of those lobes. So if it attacks from the front side, from our direction looking at it, what we end up with is an intermediate that looks like that. But of course, it can also attack from behind our molecule in that other lobe. And so if that were the case, the carbocation is still the same. But now our electrophile is on a dash. All right, so at that point, of course, we've completed our first step. We have our carbocation intermediate, and so we've got left remaining our nucleophile. And so when our nucleophile attacks, it can do one of 2 things. We've talked about how there's syn addition and there's anti-addition. And so how we want to start thinking about it is, well, this electrophile's on the front side, and so if we wanted a syn addition of this nucleophile, would we add it here on a wedge or a dash? We'd add it on a wedge. And so if we attack from the front side, our methyl gets pushed onto a dash because basically our nucleophile has come in and pushed it that way. Of course, we've still got our electrophile on the wedge on the bottom. Of course, it could also come in from the other side. Since our carbocation is planar, instead of approaching from the front, it could approach from the back. And so if it does that, what kind of addition do we end up with? Yeah, now we've got anti. So the bottom electrophile is in the same place, but now our nucleophile that has approached from the back will be on a dash, which has pushed our methyl group to be where? Yeah, now it's in the front, and that's going to be on a wedge. So what we've got is the syn product on the left, and then the anti-product on the right. Of course, we've only been adding to this product right here, right? We added from the front side of this and then from the back side of this, but we can also add from the front side of this carbocation. And so in that case, if we're going to get the syn addition and we see that electrophile is on a dash, where's the nucleophile going to be?
On a dash.
Also on a dash. And so that would be our syn addition product for that carbocation. And then if we drew the anti-product, it would be on the opposite side. And so again, if our electrophile is on a dash, our nucleophile will now be on a wedge. So that would be the anti-product, or the anti-addition product for that. Okay, so what's the relationship between all of these four products? Are any of them the same? No, so they are all stereoisomers of each other. Right? So now we can see that if the starting material doesn't have the symmetry that we had up here in this little example, we're going to find that we end up with multiple products. Yeah.
When you say like when you have like the plus between the syn and the anti, are you saying it forms both, or it's going to form one or the other?
So in this case, it's going to form both. We're going to end up with a mixture, right? And so if we were to just do this reaction right here, that we know is going to go through a carbocation, what we will end up with are four different products. There's no reason that any of these are going to be favored over the others, because everything's planar, right? We can always add to the top and we can always add to the bottom. And that's why I keep saying carbocation reactions are just really messy as hell. There's a lot of possibilities that can go on. And basically, we're going to get cleaner and cleaner as we go. We're starting with the messy stuff at first. All right. Let's see. Yeah.
So if you have a reaction like that where you can't really control which of the products you get, how would you, like, since they all do different things, since they're stereoisomers, how would you isolate a specific product?
Yeah, so honestly, what's done in the real world is not this chemistry. Yeah, we do other reactions that don't spit out four different products because it is hard to separate these things. So, for example, we've got, what's the relationship between this and this? Those are enantiomers, right? Because each chiral center is flipped. So are those separable?
No.
They're not. So even no matter what we even do, we're going to end up sometimes with products that aren't separable, right? And so what do we call it when we end up with a 50-50 mix of enantiomers? That's racemic. And so typically it's not a good thing to end up with a racemic mixture because now we have two enantiomers that aren't easily separable and we're pretty much stuck with them that way. So, yeah, in reality, we try to stay away from reactions. Good reactions are those that are going to spit out one product. Yeah. Okay, so let's do a few examples and think about what products we can end up making. So let's start out. Let's see. So let's start with a similar material. Let's treat that with HI, good old HI. So when we do so, what's our first step? Protonation of our alkene, right? We're going to start at our alkene and we're going to grab a proton. Now, which carbon will that proton add to? It'll add to the secondary, right? Because by doing so, it's joining its one friend that was already there, but also we're forming the tertiary carbocation, and so it's more stable that way. How many different carbocations can we form? Is this a chiral center?
No.
It's not, and so there's really only one possibility. If we add from the front, this is what we'll get. If we add from the back, this is also what we'll get. And so what you see is that we're not always going to form four products, and especially if we add our proton to where there's a carbon that already has a proton, we're not forming a chiral center of any kind, and so we're only going to be able to form one possible product in that case. Okay, so from here, what we're going to do is we'll have our iodine left over, and so we will snap that into our carbocation. And so, of course, we can add from the front or the back, right? So we could push this down and end up with our iodine on top, or we could attack from behind the board. And end up with that product. What's the relationship between those two products? What would happen if I took this and I flipped it over?
It'd be like
it's the same thing, right? And so what we've got is we've got one of these cases where because of the beginning, right? So what happens is we've got this plane of symmetry right here. And so basically if we rotate along that plane of symmetry, more or less if we flip that molecule over, we end up with the same molecule. So even though this mechanism allows for 4 different stereoisomers, we just have one here. It's the same product, right? And so depending on our starting material, these things can be a lot simpler than they are. Another way you can think about that, is this a chiral center?
No.
No, because if we count away, we find we have the same group going that way. So we don't even have a chiral center. So we can't have a pair of enantiomers if we don't have any chirality in the molecule itself. All right, so in this case, we have the same product. So these are the same. We have only one product. All right, so let's do another example. All right, so we'll start with a similar product, but now we'll add an oxygen to the ring. All right, so we made it a little bit different. And again, what we'll do is we'll add our HI. So I'm going to skip the mechanism because we're going to end up going through the same exact mechanism. I think it's similar enough that you can figure out what we've done. And so again, what we can do is essentially we can end up adding our iodine to the front side of the ring. So in doing so, we would have this product, or we could add it from the back side of the ring. And we end up with that product. Now, do we have that same plane of symmetry now that we've added that oxygen?
No.
Do we have a chiral center?
Yes.
Yeah, now we have 4 different groups. And so what's the relationship between these two? We've kept 2 groups the same, right? So the ring is in the same orientation, but the other 2 groups we've flipped. And so what's the relationship between molecules when we've done that? They're enantiomers. All right, so in this case, we have enantiomers. That means we have formed 2 different products. All right, so then finally another example. So actually, let's see if we can figure out what the chiral center is here. So if we look at each chiral center, we would say that's 1, 2, 3, 4. And so is that going to be R or S? All right, so we put our thumb towards the methyl group, and so we rotate that way, and so that'll be S. Over here, we've got 1, 2, 3, 4. And so in that case, we now have to have our thumb coming towards us, and that's going to be our other hand, and so that's now R. So we see, in fact, we do have a pair of names. We switched the chiral center. All right, so finally, one more. Let's start out with again, we'll go with a very similar starting material, but in this case, we're actually going to stick a chlorine right there. Okay, so again, we'll add HI, and so we'll go through the same mechanism. So again, we're basically going to end up with the iodine adding from the front of the board or from the back of the board. And so what we'd end up with would be this product. Have we done anything to the left side of the molecule? No, so that's going to just stay on a wedge. We're not doing any chemistry on that side of the molecule. And of course, we could add from the back, and so the left side will again stay exactly the same. We're not doing any chemistry, but now our iodine is on the back side. Okay, so those 2 molecules, what is their relationship? All right, so are they chiral products? They definitely are, right? They've got 2 chiral centers. So we've got a chiral center here and a chiral center here. There's not enough symmetry that we could have a meso product. So let's think about what's happening. All right, so we've got 2 chiral centers. If we look at one product to the other, are we changing this chiral center as we go from A to B? We're not. What about this one? Are we changing it as we go from A to B?
Yeah.
Yes.
We are. So if we change one chiral center but not the other, do we have mirror images?
No.
We can't have mirror images because in a mirror image, everything and so what's the relationship? They're diastereomers. There's some pair of stereoisomers that aren't enantiomers. Anything that's not an enantiomer is a diastereomer. And so again, we're going to have two products. And in fact, Lena, to your question, this chemistry would only be used in cases where we're just going to get at least maybe one product or two products that are diastereomers and are separated, because that's the only way that it's going to be a particularly useful reaction. Okay, so we're getting close to the end of our discussion of carbocation mechanisms. We're going to talk about one more thing. All right, so this would be part D, and this only applies to carbocation mechanisms, because they truly are the messiest mechanisms that we're going to encounter. All right, so what we're going to do is we'll title this carbocation rearrangements. All right, so let's define a few things. So probably shouldn't call that letter A. Let's call it number 1. So there's two possibilities here. And so number 1 is going to be what we call a 1,2 hydride shift. All right, so let's do some definitions first. So when we talk about a proton, in the sense of organic chemistry, what do we talk about? If I say a proton, what am I talking about? H plus, right? Specifically, it's an H plus. It's a hydrogen with no electrons. And so what we have when we talk about a proton is H plus. But that's not the only flavor that hydrogens come in. They also come in the flavor of hydride. And so what is a hydride? It's very much the opposite of an H plus, which would make it an H minus. And so if it's an H minus, does it have electrons? It must. How many does it have? Yeah, so if we have one proton in a hydrogen atom, we'd have to have 2 electrons to make it negative, and that's exactly what we've got. So when we talk about a hydride shift of some kind, what we're saying is we're not moving a proton, we're not moving an H+, we're actually going to be moving a hydrogen with 2 electrons, because when we say hydride, we're encompassing those electrons with it. All right, so here we go. So let's say we have a starting material that looks like this. So we're going to ignore stereochemistry for right now. We're just going to talk about connectivity. So we've got 2 possibilities, right? So, or at least I'll show you that we've got 2 possibilities. So what you might expect from everything we've learned thus far is that this bromine is going to end up on one of these carbons. Now, which would you expect it to be on? Yeah, so what's the more stable carbocation? Secondary. And so following Markovnikov's rule of that, the hydrogen to the right side, we would add our bromine to the left side. And so we'd say, well, Professor Walk, what I would expect to see in this case is addition of bromine to that secondary carbon. All right, so here's what actually happens if we run this reaction in lab. Messy, super messy. All right, so what actually happens is we form that product. How's that happen, right? Okay, so we're going to talk about how that happens. So basically what happens is, let's walk through the mechanism. So the first step of one of these mechanisms is what? It's protonate the alkene. It's always protonate the alkene. And furthermore, we're going to follow Markovnikov's rule, and so we will add that proton to the primary carbon. All right, so we go after the proton. We end up with this carbocation, which has a hydrogen right there. All right, so basically, we'll draw out all our hydrogens, or at least some of our important hydrogens here, to look like that. Okay, so we end up with this carbocation intermediate, right? We've got a secondary carbocation. But what we find is that looking at this product, we've snapped that bromine to neither of the carbons involved in the double bond. And so eventually we have to end up with a carbocation where, if we're going to snap our bromine to it. Yeah, we've got to end up with a carbocation there. And so what we do is what we call a 1,2 hydride shift. So we're going to call this 1, and we're going to call this 2. And so what we're going to do is we're going to take a hydrogen, or I should say a hydride, most definitely a hydride, which is a hydrogen and its electrons, and we're going to shift it over to carbon number 2. And so when we draw electron movement, where do we always start? always start at electrons. And so if we're going to move this hydride right here, we want to start our arrow at its sigma bond electrons. We haven't really done that before. And so what happens is we start at these electrons, and we just show them moving over to this secondary carbon that is nearby. All right, so let's think about what happens when we do so. If we undergo this 1,2 hydride shift, what we'll end up with is this carbocation right here. What kind of carbocation is this? How many carbons are attached?
Secondary.
2, so it's a secondary. What kind of carbocation is this? It's a tertiary. Why is that hydride going to move? What's going to be the driving force behind this? What reason does this molecule have, or this carbocation have to undergo this 1,2 hydride shift? It's a more stable carbocation. So what in effect we've done is we have formed a more stable carbocation. And so what we will add to that is we will say that is the only reason for a 1,2 hydride shift. That's it. Only in cases where we can move a hydride over and increase our stability. And so in this case, we've gone from a secondary to a tertiary. We've increased the other tertiary is more stable, so we're going to undergo that shift. And then eventually, what we end up with is we've still got our bromine floating around, doing whatever bromines do. And so when we snap together, we end up snapping to that carbon right there. And so we end up with that product. All right, so we can say this is not formed, or at least, let's actually just call this the minor product, because I'm sure that it does form a little bit. But over here, what we'll find is that this is our major product. Okay, so shifts, 1,2 hydride shifts are only going to occur if we're able to form a more stable carbocation by doing this. And furthermore, they're only ever a 1,2 shift. They never move further along the chain. They have to move to a carbon that's 1 carbon over. All right? Okay, so that's 1,2 hydride shifts. Messy, right? Carbocations. It gets better, I promise. All right, so next up will be number 2. And so this is a 1,2 alkyl shift. All right, so as you might imagine, it's relatively similar to a 1,2 hydride shift. Yeah.
Okay, so for the hydride shift, so the thing in the middle is what you're starting, and then you have a little bit of the minor product.
Say that again?
A little bit of the minor product.
Yeah, sure.
A little of, or more of the major product.
Right.
And then how much of the 1,2 shift?
And so the 1,2 shift, what I mean to be indicating right here is that this bottom part is the mechanism to get to the major product. And so we're only forming 2 products. I was showing down here on the bottom basically the mechanism for getting from our starting material to what we find to be our major product. That's a good question. I forgot to draw in the last arrow. Yeah?
Why is it called a 1,2 shift? What is the 1,2?
Yeah, it's called a 1,2 shift. You see where I've drawn in these blue numbers right here?
Yeah.
And so basically we say our hydride, we're going to locate carbon it's on as carbon number 1, and so we're just going to count over. So the next carbon over is going to be carbon number 2, and that's where we're going to find our carbocation. And so our hydride is on carbon 1, it shifts over to carbon number 2, and so we say it was undergone a 1,2 shift. Yeah. Yeah.
How come the carbocation is more stable with the shift? Isn't it still a tertiary carbon in some cases?
So it's still a tertiary carbon, but remember when we talk about our rate determining step of a reaction, what we found is it's determined by the most stable carbocation, right? So when we determined whether a secondary carbocation compared to a tertiary carbocation was more or less stable, we said, well, it's less stable, and for that reason, we end up seeing a lot less of that product form. Same thing here. So by doing this shift, we're able to go through a more stable carbocation, and so we end up with more of that product. Yeah. Okay. 1,2 alkyl shifts. All right, so what's an alkyl group? it's C and H stuff. So a methyl group is an alkyl group. An ethyl group is an alkyl group. We're saying any just bunch of CH stuff, that's going to be an alkyl group. All right, so we can also see situations where an alkyl group shifts. So basically, that's saying that carbons can also, say, walk over to a nearby carbocation. So an example of that would be, say, we'll have methyl, methyl, methyl. So we're going to have a very similar product. But now basically what we find is that we no longer have a hydride on that carbon that we moved last time. And so if we treat this with an acid, let's use HBr. All right, so what's our first step? Always protonate. So that's what we'll do. We protonate, we see what carbocation forms. And so that's a good first safe step. If you're not sure where to start, protonate. Form the carbocation that's more stable, and then go from there. Think about the options. In most cases, we're not going to see a shift, but it is very much a thing that occurs. All right, so when we do so, we're going to end up with this carbocation right there. So there's only one hydrogen there. All right, so we've got that carbocation. Now we've actually got some possibilities here because we do have hydrides over here. And so I guess what we could do is we could imagine going from, well, let's do a 1,2 hydride shift from that carbon and see what happens. So if we start here and we go to there, what we end up with is this carbocation, right? All right, so what kind of carbocation is that on the right? That's a primary. What kind of carbocation do we already have? Secondary. A secondary. What reason on earth would this hydride ever have to move from there to there? None. It has no reason to do so, and so we'll go ahead and say this does not happen. Doesn't happen. And it doesn't happen because this right here is a less stable carbocation. But what we could do is instead of moving a hydride from this carbon right here, we could move a methyl from this carbon right here. A methyl is an example of an alkyl group. And so if we do so, if we undergo a 1,2 alkyl shift, we've got 1, 2. And so we start our arrow for our shift where? Electrons. Always electrons. If you're not sure where to start it, a good safe bet is think to yourself, well, I've got to start it from electrons. No matter what I do, I'm going to start my arrow from electrons. And so we'll start them right, not over there, right here, from these electrons, move them over to that carbon. And so in doing so, what we end up with is this carbocation right there, which is what kind of carbocation? It is a tertiary. Is that more stable or less stable? Yeah, and so here we see a case where by moving an alkyl group, we form a more stable carbocation. And so to get onto our product, we would have our bromine snapping right to, let's see, hold on, what did I do? Sorry about this. All right, so we move that over and we actually leave that carbon electron deficient, right? All right, so what we've got here, we'll draw this out because I messed up. All right, so we've got 3 things here, and so that makes it a carbocation. If we shift this methyl group over, we're going to basically take this methyl group, move it here, which satisfies the electron charge, or the carbocation there, but then it leaves this electron deficient. So what kind of carbocation is this? Tertiary. It's tertiary. That's the tertiary carbocation we were talking about. And so when we snap our bromine in, we end up forming this product right here. Okay, so 1,2 alkyl shifts can also occur. Just be on the lookout. If you're ever going through a situation, if you're given an alkene where maybe the most stable carbocation you can form is a primary, well, we know that's not a very stable carbocation, and there's a good chance that a shift could occur. Yeah?
I don't get how the left side is.
Which structure?
The one we just did.
Oh, you mean this one right here? Yeah, I mean, technically, I guess, by drawing the plus charge, it was the same carbocation because of the symmetry of the molecule. Right?
But how is the other side not?
How is that not charged? So, this implied hydrogen right here that's still there, right? So essentially, this implied hydrogen, which I'll circle in green, it didn't move, it stayed right there where it was. And so once we moved our methyl group over, now we've got a carbon that's bonded to 4 things, and so that's not a carbocation. But over here, we're left with a carbon bonded to 3 things, and so essentially our carbocation has gone over to the other carbon. Yeah. Good question. All right. So again, a 1,2 alkyl shift occurs to form a more stable carbocation. What we'll also see sometimes is we'll have cases such as this. All right, so let's say we start with a material like this, and so we treat it with HBr. And so what's our first step? Always protonate. All right, so we've got our alkene here. And so we've got a secondary versus a primary, and so we know we'll add our hydrogen to the primary to form the secondary carbocation. All right, so we end up basically adding there, and so we end up with this secondary carbocation. And so the product we might expect to form would result from our bromine snapping in right there to give us this material. But in fact, what we see happen is, and I'm going to number our carbons to make sure that everyone can see this pretty clearly. So what we're going to do is we're going to call this carbon 1, 2, 3, 4, 5, 6. All right, so we've numbered our carbons. I think it's always a good idea, especially with what we're about to do, to number your carbons so you can basically account for all the carbons and keep track. Okay, so a 4-membered ring, when we talked about ring strain, is it highly strained or not highly strained? It is highly strained, and so what we've done is we've presented an opportunity for one of these alkyl groups to shift and basically go from a 4-membered ring to a 5-membered ring. And so in terms of ring strain, what's going to happen? Is it going to go up or down if we were to basically open our ring up more? It's going to go down. So what do you think the driving force for this sort of operation would be? It's a downhill reaction that's releasing strain. And so what we've got is we're going to undergo an alkyl shift. And so what we'll focus in on is carbon number 6. All right, so let's say that this is a highly strained ring. And so what we'll do is we'll take our alkyl group number 6 and we'll more or less shift it over to that carbocation. All right, so let's see what happens. So we've got carbons 1 and 2 here. But now what we've done is we've essentially taken carbon number 6. It's no longer connected to carbon 3. Which carbon is it connected to? 2. It's now connected to carbon 2. And so we'll say, all right, so let's count. We've got 2, 1, and 6. And then between 3, 4, 5. All right, so let's say 6 and 3 were connected. Are they going to be connected anymore? No. They're no longer connected. And so what we end up with is essentially something that looks like this. And so there was a bond between 3 and 6. It essentially has moved from 3 and 6 to 2 and 6. Where's our carbocation now? What doesn't have enough things bonded to it? What had something bonded to it in this picture but doesn't here? 3, right? And so that's where our carbocation is. And so when our bromine attacks, what we end up with is attack at carbon number 3. And we actually end up with that product right there. All right, so we can also see 1, 2 alkyl shifts with strained rings. And I've got really good news. That's mechanistically the end of carbocation talk. All the other mechanistic talk we do going forward is going to be a lot more simple. We can hesitate like a solid day and a half to spend talking about all the possibilities that can occur. Okay, I'll get information about office hours out ASAP as soon as I can schedule a room, and then yeah. Otherwise, I'll see you there for tonight's workshop at 5 in Millington, and then class on Friday.
Hi, Dr. Walk. I emailed you about this for sapling. I read through it real quickly. I'm still kind of confused because you talked about 3 being a chiral center, and I see that, but like chiral centers have 4 different groups, and I'm still having trouble kind of figuring out because this is a carbon and this is a carbon.
But what you have to do is you have to keep counting. They've got to be identical groups completely. And so if you have an ethyl group and a methyl group, those are different groups. Because one is a CH3, one is a CH2, CH3. Those are not identical groups.
Okay.
So you've got to keep counting and figure out the priorities based on the rules that we learned back when we did so.
Okay, so when also you're given priority, since oxygen weighs more.
Since oxygen has the higher atomic mass, yeah.
Right.
So it would be priority 1.
And then, so in that case, the methyl group's going to be 4, and then this is going to be 3. This carbon on the right.
So this would be 2 because this is a CH3 and
Oh.
this is a CH2 connected to a carbon.
Right.
And so now you've got your priorities.
And then, so the wedge and dash always confuses me as well. So does it matter?
Yeah, and so one thing you want to get in the habit of is here you've got a wedge going up and here you've got a dash going down. You want to make sure those are on the same side, basically. And so if you've got your line here and your line here, you want your wedge and your dash, they're good friends. They're going to stay down here. So you have a wedge here and a dash here.
Okay. So like, but for the methyl group and the hydroxide group, which is
You'll have 2 possibilities, right? Because it's a chiral center. So one could
Right.
be on a wedge down and one enantiomer, and the other will be on a dash down.
So when I'm orientating it, I orientate with the methyl group in the back.
Well, you can do either, right? So basically, if it asks you for a certain enantiomer, say it asks for the R enantiomer, you've got to figure out what orientation gives you that R, right? Basically, which will allow you to rotate your
Right.
enantiomer
And since it's
way.
a dibromo, they'll just switch and
Yeah,
be the
there's
same
no
thing.
chiral center there,
Right.
exactly.
Okay, great. Thank you so much.
Yeah, Ethan.
Okay, couple questions.
Yeah.
So when you're doing a 1-2 alkyl shift,
Uh-huh.
if you have like 2 different types of alkyls, like an ethyl and a methyl,
That's a good question.
which one shifts?
I'm trying to remember the rule to that. I think the bulkier one moves, but we're not going to get into that much,
Okay, so-
much detail. There are rules to it.
Would there ever be a situation where you would have to choose between like a hydrogen shift or an alkyl shift at the same time when they're both?
So typically what you'll see is a hydride shift is less costly energetically. So I'll tack that on to the beginning of next time's lecture. I'll say that if you can do a hydride shift, you're going to do that. You're typically only going to see an alkyl shift when you can't do that.
Okay. And would there ever be a situation in which it would be like favorable for there to be a hydride shift to say 1, and then it's also favorable for another hydride shift to happen again?
Yeah, I mean that stuff happens for sure.
Okay.
But we're not, I got to keep it simple.
Okay.
That's complex stuff. A lot of products get occur when that happens.
Okay.
Yeah.